Okay, so I want to show you how one uses this theorem 2 on a very concrete example. So I always look at my basic example, which is equations of this type. We have a number field K. And then the Pi of t are irreducible. And say Pi, and they're not proportional. So Pi over, let's say, irreducible. So let me put a constant C, in K star. A is in K star. C is in K star. Pi irreducible monic. And Pi is different from Pj. Fi is different from J. Okay, and so remember, I showed you a statement when we have just one irreducible polynomial. I said that using Schinsel, you prove the local global principle. Now we look at the case when there are several polynomials. We saw that when I have two polynomials of degree 2, we may have a counterexample to that principle. Okay. So now let's take, so this is this. I look at the open set where this is different from 0. This is my U.
So,
yeah.
So the upper index from I to 1 to R.
1 to R.
Okay.
So I have R polynomials.
Fine.
And yeah, okay. And this is so the variables are y, z, t. Okay. The surface. Okay. So we look at U, and then we look at the smooth compactification, which one may write explicitly, which I don't do. And then the claim is, so the theorem is that if Schinsel hypothesis is true, then I'm going to prove this right here. Then x of k top is equal to x of ak bar x. Okay, so proof. Well, we introduce a group B in the bar of U, which is the group spanned by the elements A, comma, Pi of t, the quaternion algebras. Okay, so these are quaternion algebras. On U, Pi of t is invertible, so this is an element at bar of U, but it need not belong to the bar of X. It could have a pole at infinity. It's like if Pi is of even degree, there's no problem. If Pi is of odd degree, there's a problem. But that's a detail. Okay? Just define P like this. Okay. Okay, and then so take a point MV in X. Okay, maybe Wednesday I should say here. Okay, let me be precise. So here, one can check, and I will not do it. One can check that bar of X divided by bar of K is finite. In fact, you can check it by using this formula I gave you for the bar group of a vibration into conics. So I discussed that last time. You can check this. Okay, so now start with points MV. So take points MV, V in omega, and x of kV. X of AK orthogonal to the bar of X. So this, because bar of X over bar of X is finite, we take finite representatives. So let's say alpha, so this is different. So this is beta I here, alpha j. Suppose alpha j span the bar of X divided by bar of K. Finitely many. Okay, so because this quotient is finite, I can represent it by finitely many elements in the bar of X. Okay, and then these elements in the bar of x, they vanish on x of kv for almost all v. Okay, so from this I find that may replace mv by a family pv in u of ak. Okay, whereas pv minus mv is smaller than epsilon in a sense which is clear for v and s. S is finite. S is a finite set of places where we want to approximate. So I can move, because you see the alpha j is constant on is 0 on x of kv for almost all v, and it's locally constant. So that if I move for a given v, I can move my mv a little bit, and I do not change the value of alpha j. Okay? So I can push my element mv into u. And then for the places which are within the bad set for this alpha j, I can pick up any PVs, I don't care. So now I have my PVs which are in u of ak. So I can replace this mv by this PV. Okay. Now this u, it's in u of ak, and it's orthogonal to bar of x, because initially we were orthogonal to bar of x. Okay. Now look at the theorem here. We have PVs in u of ak. And we assume that for element in the bar group, in the total bar group, it's orthogonal. Okay? So we apply the theorem here. So we find that there exists, apply it so by a formal lemma, which in this case can be proved very easily. We find that there exists some points let's say p dash v. In u of ak, where p dash v is equal to pv for v and s, and this time for all betas, sum of beta I of p dash v, v in omega is equal to 0. Okay, but so what does it say? Now look at the sequence we have k. So the p dash v's are given by yv, zv, tv. TV, yeah, it's tv, okay. And so what we have is that, and then we look at the exact sequence, k star divided, so capital K is k of root a. And with this exact sequence, k star modulo norm k star, direct sum from class field theory, v in omega, of kv star divided by norm capital Kv star goes to z mod 2, which is a subsequence of the sequence bar of k goes to direct sum for all v of bar of kv goes to q mod z. And so we have, if I write the condition here, sum of pi, what does it say here? Beta I is given by, so this is sum of the a comma pi of tv, v equals 0, v in omega. And now this is saying that if I take the classes pi of tv here, and I push them here, I get 0. So this equation here, sum of a pi of tv, v for all omega is 0, is simply saying, if I transcribe it in terms of kv modulo norms, it says that the family of pi of tv is, the sum is 0 here. And now we use something very crucial, which is not only, so when you want to look at counterexamples as a principle, you use the fact that the composite is 0. You use reciprocity. But here we're going to use something stronger from class field theory, saying that if a sum is 0, then in fact there exists somewhere a global element that gives them. So this is really a crucial point in many arguments in this theory. So that implies that there exist elements Ci in K star, such that the system of equation Pi of Tv equals Ci, and then I'm going to write the equations Uiv square minus A, Wiv square, different from 0, with a point which is on the variety. So we have y square minus A z square equals C product of the Pi of T. So there's a solution for this for all. So I look at this equation. P of t, sorry. I put ui square here. I look at this here, P of t. And then what this implies that there exists Ci in K star such that this system, which projects down to y square minus az square equals C product of Pi of t, has a solution in all KVs. So we produce an auxiliary, so we started with a variety, and we produce an auxiliary variety, which is a much bigger dimension, which projects down to the original one, and which is global, the Ci are global, and it projects down to this one, and it has points in all completions. That's the point, yeah. Because the Ci goes to this class Pi of TV. Okay. So that's the key point here. So the variety is given by this set of equations. And it maps to this one by just forgetting the first one. You see, we produced, for the TVs, we know that if we take YV, ZV, TV, there exists a solution to Pi of TV equals Ci times the norm, locally at V, for each I. This was our conclusion. So that is saying, if you look at it another way, it is saying that if I look at this, the variety defined by this, all these the equation, the variables are y, z, t, ui, vi, wi, sorry. This has points in all the completions. And there's points in all the completions, mapping down to the local points I was given at the beginning. Okay. And now we look at this equation here. Now there's a small miracle which happens, which is that I can plug in, you see I have these norms here, and here I have this norm here. So I can push them inside the other one, and then it breaks up as a product. So changing variables, change variables. And you find that the variety, let's call this variety. So this was our U here. This variety is called VCI. We find that VCI is isomorphic to what? Y capital Y square minus AZ square equals C product of the CI. And then I keep on the other equations. UI square minus AVI square equals C times CI. Well, let's put this CI here. Okay, CI here equals, okay, let me put the CI on the other side. Equals Ci Pi of t. Okay. Because I can write, I can write y plus root az equals product of the what is it? Ui plus root avi. This is a change of variables. Okay, so the variety has become the product. Now the variables are separated. Here we have a conic. And here we have this variety given by these equations where the Pi now are irreducible. Okay, now we conclude because here we have Hasse principle plus weak approximation. And here we have that Schinsel H implies here Hasse principle plus weak approximation for this equation here. So what we proved is at least that there is a rational point modulo Schinsel. We found that this variety has a rational point, which we push down to a rational point downstairs.
Once again, sorry.
Yeah.
So for the conic bundle, we have for the conic. Yes. For the
conic, well, you have this is a constant. So Hasse principle weak approximation holds. Okay. Yeah. And for this other one, what I explained last time, but you were not here, is that at least if you have one irreducible polynomial, an equation like this, we suppose R was 1, this satisfies the Hasse principle. But the argument is the same if I take a product. I mean, roughly speaking, says, no, I can explain. Roughly speaking, what happens is suppose one has solutions that are locally, then one approximates Schinsel hypothesis will enable you to approximate the TVs by a suitable T0 such that each P of T0 is essentially a prime times some other primes which are controlled. That is this equation, so that you'll find a T0 so that this equation, this system has solutions in all completions except possibly one prime for each Pi. But then a conic which has a point in all completions except one has points everywhere. So each of these, so you have this product of conics, and each of them has a point. By using this key argument that a conic with points in all coefficients but one automatically has a rational point, which was Hassel's insight. Okay. So that's okay. So that explains this, and then this so the generalization, so the general theorem along this line. So the most general theorem along this line. So I'm going to write it down. So I showed you a special example so that you understand how the formal lemma is used in the proof, but working hard when prove the general theorem. So this was, okay, it is a long story, but okay, there's various names. You can look at the papers. Theorem is this. Suppose you have x goes to P1, a fibration. Assume 1 Hasse principle plus weak approximation for the smooth fibers. Here we're at conics, so it was clear. 2, assume that for all points m in P1k, there exists a component y in the fiber at m. So all the close points. Okay? There's a component m of multiplicity 1 with K of m with the algebraic closure, so K of m, sorry, with such that the algebraic closure, I'm repeating something I said last time, I think, of K of m in the function field of K of y is abelian over K of m. And then assume 3 Schinzel's hypothesis. And then the conclusion is that for the total space, then x of k top is equal to x of ak bar. So the conjecture is true. Okay. In other words, for a variety which is like this. So which is fibered over P1. The fibers satisfy as a principal numeric approximation, and then this condition that for all close points there's a component multiplicity 1 which is split split over IBA extension of the ground field, and then Schinzel's hypothesis. Okay, so this generalizes what we just saw, okay? And so there's the criticism for this is the double criticism, is that the criticism is that, well, there are many criticisms. The criticism is this abelian condition is very nasty. So for instance, you get families of cerebrals are fine, because there's cerebral is split over, I mean, if it degenerates, you get some cyclic extension that measures the degeneration. Just like conic bundles, you get this quadratic extension. For cerebral, you get a cyclic extension for the bad fiber. So that's fine. But if you take a family of depth of surface of degree 6, so depth of surface of degree 6 satisfied as a principle, one cannot apply this result. Okay, so this is one criticism here. Another criticism is that we're assuming it has a principal recapitulation in the fibers. So the ideal theorem would be, suppose that in the fibers you know that the conjecture is true. Is it true for the total space? So you will have possible counterexamples in the, so that's another criticism. And then the third criticism is that Schinzel's hypothesis is a big conjecture. Okay, so now, so what I wanted to be in the algebraic part, but maybe I'll stick to the arithmetic part for some time, maybe for the rest of the time. Depends what you want to listen. Anyway, I have time to cover the arithmetic part I wanted to cover, so that you can see that there are actual theorems that come out of this story, not just conjectural theorem with this. Okay, so this is the story with what happened with in additive combinatorics. Well, we're going to use Harry's formal lemma again, but so Harry's formal lemma is really something. It took us a long time to think of using elements of the Brauer group of open sets. We're always using the Brauer of the smooth projective model, and we're really, afraid of using the elements of the Brauer of the open set. In fact, they're very useful. and it much of the theory of descent, which Sanjay and I had developed for smooth projective varieties. To some extent, you can get many of the results by forgetting torsors and using Borel group of open sets. That's okay. So now, in the arithmetic I want to discuss now is how, in some cases, you can use the same arguments and get unconditional theorem by getting rid of this. Okay. So this is Green. So this is the work of Green, Tao, and Ziegler, which is 2010, and then there's further work of these three in 2012. Okay, so here's the theorem. So let me tell you that what I'm going to say now is entirely contained in a very easy to read paper by Harpaz, Skobokatov, and Wittenberg in Compositio, 2000, maybe 2014 or something like that. Okay. So, what is the theorem of Green, Tao, and Ziegler? I just reproduced from their paper. So you take Li of x, y, linear forms in Z bracket x, y, linear forms, and Li not proportional to Lj for I different from j. Okay, so they're not proportional pairs. And then you take elements Ci in Z. And they assume that for all prime P, there exists Mn in Z square, so that P doesn't divide the product of the Li of Mn plus Ci. So you look at, actually you look at an additive, an affine linear form. So this one is homogeneous, you add a constant, okay? So you take something of the shape Ax plus By plus C, okay? So you're interested in these elements. You want to say something about the values of this family of elements. So you don't want a prime P to divide all these values. It's the same condition as the condition I explained last time. You're not asking that x plus 2, x plus 4 represent infinite many primes, because one of them is divisible by 3, and so there's a problem. So you evacuate this problem, you put this condition. It's a very natural, very simple condition. Assume this, okay? And then you have k in R square, which is a convex and open, which is given to you. Okay, convex open cone. Well, let's say convex open cone. Okay, and assume this is also that there exists Mn, such that each Li of Mn is positive. Again, it's a condition like if you want a polynomial which is reducible to represent infinite many primes with this plus sign, it's better if the leading coefficient is positive. So it's really a very simple condition. It's something about the coefficient, so that you, okay. So that's, and then the theorem, and so this is the amazing theorem, is that then there exists infinitely many pairs of integers, Mn in Z square, such that in fact in Z square intersection this convex open cone, so you can put them in there, such that each Li of Mn plus Ci is a prime. Okay, that's the conclusion.
For each cone we have
any convex open cone. So if you forget about this condition, suppose you took you wanted well you could take whatever convex open cone. Well, if you forget this condition about the reals and you put the Ci to be 0, which is allowed, you're really looking at A1x plus B1y, A2x plus B2y, A100x plus B100y, and the same is that unless there's some stupid obstruction like this one, there are infinitely many pairs of integers mn such that a1n plus b1n is a prime, a2n plus b2n is a prime, a100n plus c100n is a prime. And this kind of theorems that were known only for two forms. In fact, I think Green and Tao first proved a theorem like this for 3 forms, 4 forms, and at some point they said, we can do any number of linear forms. So it's really quite a striking theorem. It's an analog of Schinsel hypothesis, except that you have 2 variables and that you restrict yourself to linear things. But still, it is quite amazing. So the idea is that of the paper now is that once you have an analog of Schinsel hypothesis, well, you develop the analog of the arguments which we had before with Schinsel, and you see what you get. And so, I want to develop it a little bit because there's an amusing argument with Harry's formal lemma at the end. So this theorem, so the Green-Tao, in fact, this thing is already in Green-Tao 2010, implies. So I should say that there's an earlier work here with Matheson. I'm the first people who saw that there's a paper of Browning, Skorobogatov, and Matheson. They were the first people to see that you could use Green-Tao to get these results about Hasse principle. Okay, but then afterwards, these people here wrote a paper which contains the content is in fact more powerful. But they first had the idea here. Okay, so the Green-Tao implies, in much the same way as we had Schinsel over Q implies the result which Serre had developed, implies something more flexible. So the theorem is this, but it's an easy consequence. Suppose, given lambda p mu p in QP star, in QP square, for p in a finite set of places, S is given. Okay, and given and C positive. And then you have elements E1, ER, which are in Z of 1 over S, if I dare say. So the denominators are only in S. Okay, and then the statement is that then there exist infinitely many pairs, lambda mu, in Z 1 over S, such that one, this is to take care of the real place, bigger than 0. 2, lambda mu minus lambda p mu p for the p-adic distance is smaller than epsilon. Epsilon is given, say, 1 over c. And then 3, this is where you recognize the statement over there. Lambda minus ei mu is of the shape pi ui, where ui has only primes in S. So it's just product of primes with positive or negative exponents, but only in S. And pi is a prime. And pi is different. So let's put ei different from ej. And if pi is different from pj, for I different from j. Okay, so it's a very formal consequence of that theorem over there. But it takes 1 page to prove it, but it's elementary. So elementary. So you're approximating. So you're looking at pairs lambda p mu p, and you want to approximate by a lambda mu, and you want the lambda minus ei mu to be nearly prime, except for the bad primes which are given at the outset, which you cannot avoid. Okay. Okay. And then. And then the theorem is that, and now this is an equational theorem from you see in the paper. So suppose you take k over k equals q of root a, and you take elements bi in q star, elements EI in Q, EI different from EJ. And then you look at the system of equation BI, U minus EIV equals UI square minus AVI square. In fact, I'm going to be more general. I take various cyclic quadratic extensions. So I look at, on the left-hand side, I have this linear forms in U and V up to a constant. On the right-hand side, the norm from these quadratic extensions. I range from 1 to R. So U and V are variables. UI and VI are variables. Okay? And the capital K is Ki. It is K of root AI. Okay? So I look at this.
And this is not BI, this is BI times.
Yeah, AI times VI square.
No, BI times the parenthesis, what is written in parentheses.
Here, Q of root AI.
No.
Sorry, BI times U minus EIV. Okay. So we look at the system of equation like this. So arbitrary number. This is over Q. There's not over number field, it's over Q. On the left-hand side, we have this form U minus EIV. On the right-hand side, there are these norms of quadratic extensions. Okay? And then the theorem is that this equation satisfies as a principle plus weak approximation.
Yes, this system of equations.
This system of equations, yeah. The system. So if you compare with what we had before, we had norms of quadratic extension, one quadratic extension on the right-hand side, and then we're typically, even in the case when, so suppose if we started from y square minus az square equals product of lambda minus EI, in the end we get equations like BI times U minus EI equals UI square minus AVI square. Okay? But there was just one variable. Now we have two variables here. Okay? Okay. And for this system, and so I prepared this, but you can imagine that it's not hard using this to get this result. Where's the two variables? Because there's two things here, lambda mu, okay? Here we have UV. So it's not hard to see how, by the same arguments as the one we have seen before, if you accept this, you'll get that result. And so the proof will be, the proof in the end uses the fact that a conic uses that if C over Q is a conic, product of C of QP, P different from P0, but P also not empty, and C, where P could be infinity, implies C of Q not empty. So again, this is uses as a straight that a conic which has points in all completion but one as a solution in the last one and in the global field in Q. Okay. So same type of proof. But then at least I will finish this part, and we'll see whether you want me to stop afterwards, by showing you how one can actually get something with just one variable instead of two. So here's a beautiful trick. So here's a theorem. Consider U given by over Q. For example, the green towel, for the time being, they only get results over Q. Okay, U over Q. Consider equation y square minus az square equals product of x minus EI, IN from 1 to R. This is over Q. EI in Q, say EI different from EJ. And A is in Q star. Then you take a smooth compactification. And the claim is that x of Q top is equal to x of AQ bar x. So, now you see, if I take a smooth, of course, if I take different from 0, I'm okay. But if I put 0 here, I would see an obvious point. I would see obvious points on this surface because I can take x equals EI and then y equals z equals 0. So on the obvious model, there are some obvious points. Finitely many. Okay. So the issue here is not to decide whether there's a rational point. The issue is to decide whether weak approximation is completely controlled by the Brauer group. Okay. Note that this thing implies that x of q is Zariski dense in x and the surface x. Whereas all we knew was that there were finitely obvious rational points. So there were finitely rational points, and a priori, this could have been the only ones. So it's absolutely amazing that this thing here produces an enormous quantity of rational points on your surface, which we didn't know how to prove. See, for R at least say 10. So here, if you take this surface, R equals 10, no one had the idea whether these things are unirational over Q. So one doesn't know whether the rational points are Zariski dense. This is the first proof.
Okay, yeah.
Another way people looked at this is you take a quaternion algebra over Q of t. And you ask whether the infinite Q of t, Q parenthesis t. And you ask whether the infinite values of the parameter t, so that when you evaluate your quaternion algebra, you get 0. Okay, that's a difficult problem.
Is it open?
No, well, in this case, it's closed.
It's closed.
In this case, when they split. But if I take even over Q, if the problem is not split, then we don't know. Okay. So how does one prove this? So this is a trick I like. So proof. So we want to deduce this from that result over there. Okay. But before, when we're looking at the equation like this, we reduce to equations like this one, with just one variable here. Now we have two variables here. So how do we get rid of this? So you introduce, I don't know how it works, but why it works, but it works. Introduce two variables, right? X is u over v. And say for simplicity, may assume that R is even. Assume R even. Okay. A number of the R up there is even. Okay. So you plug this into the variables, then you get equations y squared minus az squared. Change the variables, you get y squared minus az squared equals product of the u minus eiv. I range from 1 to, so R is 2R. R equals 2s. 2s. Okay, and of course I wrote this equation here. So what happens is that if I look at this variety here, call it W, I have that W is isomorphic to GM cross U. Okay, it's bigger, but it's isomorphic to GM cross U because I make this easy change of variable with V different from 0, V invertible, okay? V in GM. So now, W is given by this one here. No, this system. It's always, I don't like when it's 0. So W is given by this. I take the open set where this is different from 0. It's this business of writing different from 0 was something for which we pointed out from the outset is to get a smooth variety. Then you take a smooth compactification, and this one might be singular. So that's why you put this different from 0 here. So now, okay. So now if I take so U at a compactification X, and then W, I produce some compactification Y, smooth compactification. And then Y is birational, which is now projective, is birational to P1 cross X. And now the Brauer group doesn't change if you have between smooth projective varieties, which are birational, the Brauer group is the same. Brauer Y is equal to Brauer group of P1 cross X. So if you start with your points MV, which you may assume, say, in U are in U of AK Brauer of X, well, they actually come from points PVs, which I can take in a very obvious fashion. I take MV, comma, the point 1 in GM. And this PV now belongs to W of AQ, Brauer group of Y. I'm using the fact that the Brauer group doesn't change by smooth projective. So I have this MV, which I given before, and I introduce, if I took V equals 1, this gives me points on this variety, which project to the other one by this map. Okay. But now, use Harris formal lemma for the family U minus EIV, comma A. So now these are invertible functions on W. A is this constant. This belongs to the bar group of W. Okay, and if you use Harris formal lemma for this thing here, then by the same argument as before, you get elements. So I hope I'm going to get the same notation as before, where you get elements Ci in K star, such that the system U minus EIV equals Ci, let me call it UI square minus AVI square, and then capital Y square minus AZ square equals product of C of U minus EIV as solutions in all completions. Okay, the same argument as using. So we produce by this. So we produce CIs in K star, such that the system given by this, which is above this variety here, has solutions in all the completions.
The product is taken up to the product.
2S, yeah, 2S, yeah, 2S. The product of the U minus IV here. Okay. And again, this thing here is isomorphic to U minus EIV, and I can put a different from 0 here. Is isomorphic to U minus EIV equals Ci times U capital UI square minus A capital VI square. Different from 0, sorry. Product, well, I get this conic. I put this into there, I make the change of variable, product of conic Y square minus Z square equals C product of the CI. So using Harris formal lemma,
Wait a bit.
yeah. So using Harris formal lemma, out of these elements in the Brahmanin set of this bigger variety, we produce global CIs using the reciprocity sequence in class field theory, such that this system has solutions in all the completions. And that system, by this obvious change of variables, is isomorphic to this product here. Now we have a conic, and now we have this equation here, but this equation is precisely what, I hope it's still there, what this theorem gives us. So now we've gained one variable. Instead of having lambda minus Ci on the left-hand side, we have this U minus EIV.
So the conclusion of this
Applies.
has a principle. And
So it has a principle, so you get rational points in this, so you get rational point in this one, so you get...
I mean, has a principle and with a
Yeah, you get has a principle and weak approximation.
Yeah.
And so you started with your family of local points on W, which you've lifted to a family of local points here, and now you produce, and then above this you produce another variety with local points above for the V in S, and now upstairs you find a rational point close to this ones in S. You push it down, and you get you're happy in W.
Okay.
I mean, there's a miracle here. I mean, how setting x equals u over v, you can gain something. It's very strange, but it works. And the affine line has no limit to its use.
I have no limit. Go ahead, small request. So there is this W, there is this GM cross U, and
Which is gotten by the V.
Right. And there is a variety above GM cross U.
So you have, there's
What is this? I mean, name of this variety or
W is this one. W is this one here. This is W. This is W. W is this one. And above this one, we have this one. So we produce this one, which is isomorphic to this product. That thing is isomorphic to this product of these two. and this one is the one on top of W, which we created by using Harris formal lemma.
Which one is over top?
This one, I mean, Harris formal lemma gives us some CIs such that this system has solutions in all the completions above the given local things which were given on this one, and which is W.
This is W. Okay.
Yeah.
My problem was this. So, with the geometric picture, it seems I got the arguments, but I didn't get the relation precise relation between all three varieties and the equations.
So, the one we're interested in is this one. Okay, that's the one we want because it's a surface. It's a very nice surface. Everybody wants to know about this surface. Okay, that's
sure.
I mean, it's been for 40 years, 50 years, people have been asking this question. Okay.
Yeah.
So now, you want to find lots of rational points on this surface. In fact, close to given local points, which are orthogonal to, provided your family of local points is orthogonal to the Barrow group.
Yeah.
So you do this magic trick of making the variety one dimension bigger.
Making variety of one dimension.
Then bigger by introduce two variables, u and v.
Is of dimension 3?
There's dimension 3, yes. Yeah, dimension 3.
Yeah.
This one is dimension 2. This one is dimension 3.
Okay, yeah.
So it's because, I mean, you have 4 variables here, y, z, u, and v, and one equation. Okay?
Yeah.
So this variable dimension 3. Okay? And then it's because it's birational to this one, up to some scalar. Any family of local points which is, so I mean I can write the diagrams if you want, but I just repeat.
Yeah.
So we'll start with x, which is of dimension 2, and then replace this by some variety y, which is of dimension 3, but which is birational to P1 cross x. Okay, and then the family of local points MVs, which are orthogonal to the Barrow group, they come from some family NV here, which is orthogonal to the Barrow group here. And then using the fact, so this is in the Barrow-Manin set. Now, using the fact that it's in the Barrow-Manin set, one produces a much bigger variety, say Z, which is of dimension, well, in this case, it's going to be a dimension 3 plus R, and points P-V here, mapping to MV. And really, there are local points mapping to MV. And the Z is defined over K. Okay? And this one projects to X2. And on the open set, actually, it's a morphism. Birationally, but on the open set, different from 0, it's really an isomorphism with, without exception. Okay. And then, I mean, we produce this Z by using, I repeat, this fundamental sequence K star by using Harris formal lemma plus the exactness of the sequence K star goes direct sum KV star, norm KV star goes to Z mod 2. So if I have a family which goes to 0, there's some global element there. It's the beginning of producing some auxiliary variety. So that's how you get this Z here. And then it comes equipped with these P-Vs, which map to the NV. And now you look at their equation. This is the equation of Z on the open set.
These are the equations of Z.
So the Y is here, and the Z is given by this U minus EIV equals the constant times the norm for each I. So this is fibered over this variety. In fact, it's a torsor under R1GM to the power, but never mind. And now, if you look at this, you can make, because U minus IV is equals C times the norm, if you plug it into here, you see you can make a change of variable, and it becomes isomorphic to this one which you keep, but this one you transform into simply a conic.
Okay, and
so it's a product of this one and this one, but this one, the Green-Tao, Ziegler, Harpas, Corbocata, Wittenberg tells us that for this one, as a principle and weak approximation are okay. So we can find a P-0, so there's a P0 which is close to the PV. This is Harpas, Corbocata, Wittenberg. Okay, and then this big. Rational point, yeah, rational point, yeah, yeah. Okay. And then this rational point, well, now you push it down to this one, and you get the rational point down here, which is close to the original thing you started with. So you have these local points on this global variety. You produce an auxiliary variety, much bigger, with a projection out, which is, there are many possibilities. In fact, the possibilities are to various CIs you could choose. Huh? But you can find some precise CIs such that the local points actually come from each local point comes from a local point on this global one.
So my question, the question is, these CIs,
yeah.
So they are produced using Ethereum.
We're using this.
So this is global.
Yeah, so Array's formal lemma gives you elements here which add up to 0.
Yeah, right.
And then you say, okay, now I remember class with theory.
Yeah.
I know that these local things, actually I can produce some global CI here.
Some global CI.
CI. For each I.
Many.
Well, modulo norms. But
no, I mean for each I.
For each I you can produce a CI. Yeah, because you got some of the pi of TV A V in omega equals 0. This is what Array's formal lemma gave you. So you put this pi of TV here, and this says the sum is 0, so you produce a global thing here. Here pi of TV is simply a UV. In this case it's UV minus EI VV. Sorry. Okay. Sorry, there are two V's.
So this variety C.
This variety.
The variety Z.
Yeah.
Let's see. So it's given by two families of equations, the right-hand side and the left-hand side. But if you forget about equations, so we use equations on the right-hand side.
Yeah.
To produce P prime V.
To produce the P prime V on this variety, yes.
Yeah. But then we use another form of this.
Yeah, there's a miracle. In fact, there's a second miracle here, is that a priori, if you do this kind of operation, you get the torsor over some variety under some torus. There's absolutely no reason why this torsor should break up as a product of two things.
Right.
It just happens in that case. But
it is doesn't mean that this torsor is trivial.
No, it's not trivial. No, it's not trivial. It's not trivial. No, it's not trivial. It's just that, how shall I put it?
But it is a product of, this is a constant.
Actually, it's the product of the torsor. It's a torsor over this conic times A2.
Okay.
But still, it's still a torsor. It's non-trivial torsor.
Non-trivial, yeah.
So the thing which is miracle is that you split off this conic and get away. It's more than, if you look at this equation, as fibered over UV, UI, VI, it's a family of conics, but that conic itself is constant.
I try to formulate myself.
Yeah.
Yeah. So you have my impression that So the basis of these two torsors are different ones, right?
Yes. I mean, the basis of this, the basis of this torsor here is this surface here, this threefold, sorry.
Yeah.
And here, the basis of the torsor would be the product A2 cross this conic.
Okay.
But I think we shouldn't be too obsessed by this because it's. I picked up this example because it's easy to explain.
No,
but it's a general.
So there is geometry and there is deep arithmetic here, very deep. But also there is this. There's funny geometry here. I mean, even the idea of introducing this x equals u over v is strange. I mean, it's very beautiful.
But the thing is that the gel. So I told you that if you use Schinsel, you can prove some specific case of this local global principle. And I told you there's a gel statement, the one which was here. I hope it's still here. It's not. No, it's not. No, sorry. The one which was here before. for arbitrary families when the Hasse principle recapitulation hold in the fiber. I mean, here, the Harpaz, Skobrakov-Wittenberg result, you can find more general statements starting from Green-Tau than the one. I choose a simple one because one sees the equation. But basically, if you look at the family, for instance, of cerebral varieties over P1Q, such that the only bad fibers are above rational points, then the same argument will work. Okay, so it's more complicated.
In fact, I would say that I more or less understood the arithmetic which is involved.
Yeah.
But this geometry,
yeah, it's very strange.
And
well, no, there's one thing. Maybe there's one thing I can say. Okay, is that okay? No, I can say one thing, which is the following: is that you can. Okay, this is a conic bundle over A2.
Over A2.
A2. And this conic bundle, if I look at YZ, this is fibered over A2. So we have a conic bundle over A2. Threefold is conic bundle over A2. It's got some ramification locus.
Okay.
Now, if you do this thing here, you do a torsor over A2, which also is badly ramified exactly in the same place where this one was. And so you use Abianca's, so there's a big basic motto, which you should all know, is Abianca's theorem, which is that ramification kills ramification.
Okay, yeah.
So it's so the typical case is, suppose you take a p-adic field, and you take QP of root P, and you take QP of root of a unit times P. So both are ramified. But if you compose, you get QP of root U. The next one is unramified, so you've killed the ramification. Each of them was ramified. When we go up there, it becomes unramified. So this is a very basic principle in algebraic geometry that ramification kills ramification. So it's got various variations. It's called Abianca's lemma. I always forget this. No, I'm not sure about this one. No. H? Maybe there's an H here. So anyway, here. So you see, this one is fibered over A2. A picture?
In picture. No?
Oh yeah, I can draw a picture.
This is a kind of at least geometric argument. So one could try to get it.
But I repeat, it's something special to this situation. But anyway, so no, y square minus z square. So let's see. There's UV. There's A2 here. UV. Okay, and here. Okay, here I have y square minus az square equals product of the u minus eiv. 1 to 2r. So this is ramified along these various lines. And on the other hand, I have this one here, where I write that u minus eiv equals ci product ui square minus avi square. I range from 1 to r. Okay. And now that each, if I just looked at one variable, this one is ramified along u minus e1v. So I get something which is also ramified along exactly the same thing.
Exactly the same.
And then what it happens that if you take the fiber product, somehow the ramification is killed, and so your conic bundle here, which is given by this equation, becomes constant, becomes unramified. And so it splits. It's killed, and then you have a conic bundle over something which is rather nice, and which, for some reason which I don't understand completely, it's not obvious because this is a complicated. Even that is a complicated variety. You see.
Sure.
This variety is it's an intersection of quarks. If you eliminate the u and the v, if you have many i's, you get an intersection of quarks. So it's not at all clear why. In fact, it's not clear, but this is something funny. These people in number theory prove theorems for you that some varieties satisfy the Hasse principle. So for instance, they prove for us that these varieties satisfy the Hasse principle, essentially. But then you say, this is bizarre, because there can be no counterexample. So it must be that the Brouwer group of a smooth model of this is 0. But it's not clear how to compute the Brouwer group of a smooth model of this. So you have a new challenge. How do you prove purely algebraically that the Borg of this thing is 0? The unverified Borg group. So in fact, if one can actually prove it, one can prove purely algebraically that the unverified Borg group. I did this. In fact, I was shocked. It was the first time. Normally, it's us. We tell them we compute the algebra. You should prove the arithmetic. But now they prove the arithmetic, and it must be that there's some algebraic reason. Okay? So one can compute that the Borg of a smooth projective model is trivial. So if you take your conic bundle and you pull it back here, you can check that at least it's unverified in the algebra is unverified everywhere. So at least it is constant in the Borg group. It still doesn't mean that it's a conic.
Yeah.
Because a number which is constant need not be represented, but still it's close to it at least. So I try not to give many proofs, just main statements. So this is chapter whatever. I think it's chapter 6. So now if I count the number of lectures, this is computing some Borg groups. So the basic problem is given a K variety. So K is the field of characteristics 0. Given a K variety, U, and a smooth compactification. So U is given, but you do not have the smooth compactification explicitly. Compute. Even sometimes you have X, but you don't know how to compute Borg of X. Okay. So I want to say a few things. So first of all, if X bar, which is X cross K bar, is rationally connected, then Borg of X divided by Borg of K is finite. Okay, so how does that go? Well, first of all, peak X bar is free of finite type for a variety which is rationally connected. Basically, what is true is that if you take a rationally connected variety, it has no finite étale covers. That's a basic theorem. A rationally connected variety, there are no finite étale covers, just like for P1s. No, non-constant, of course, so no irreducible finite étale covers. And from this, you get, in particular, that Picard has no torsion. Okay? So this is one thing. And out of this, you get that H1K peak X bar is finite. H1 of Galois within peak X bar is finite. And then the transcendental part of the Borg group, I told you that there's an extension. You have the Q in general for any variety. You have Q mod Z to the power B2 minus rho. This is over C, but one can do it over algebraic equals field of characteristics 0. Goes to Borg of X bar, goes to the 3 torsion and the Betty, G Z. Okay. So that is finite, the torsion in H3, of course. And here, this thing is 0 for a rationally connected variety, because that thing is equivalent to H2 XOX is 0. This is vanishing here. If and if this one is 0, and rationally connected variety have the property that all the HI XOX coherent are 0. I bigger than 0. Okay. So we know that the transcendental part is finite, and then this one is finite. And I remind you that we have this basic exact sequence, Borg of K, Borg 1x, H1K peak X bar, H3K GM. For any smooth projective geometrically connected. And Borg 1 is the notation for the kernel of bar of x goes to bar of x bar. Okay. So in fact, there's an amusing fact, but I won't have time to explain that. In fact, if x over k is geometrically is rationally connected, so which means over variable closure, then there exists a positive integer and positive, such that for any field f containing k, bar of x extended to f divided by its constant part is killed by this positive integer. So it's even stronger than saying that it's finite. Well, it's killed by some fixed integer here. It's quite an amusing argument using the generic point, but I won't go into that. Okay, then I want to, this is John's fact here. B. One thing about completed sections. So if I take a completed section x d1 dr in projective space P capital N, where this is degrees, so this is a fi x0 xn equals 0, I ranging from 1 to r. This one is a degree di, and it's a completed section. If the dimension of x is at least 3, then bar of x divided by bar of k is 0. So this is quite a puzzling situation because I didn't put any condition on the degrees. So if n is bigger than the sum of the di, then x is final, and so it is rationally connected. But in arbitrary degree, as soon as we have a dimension at least 3, there is no Brouwer group. So for instance, if I take in P4, I take a hypersurface of degree 100, smooth. I do not see anything with the Brouwer group. I don't see any abstraction to the Hasse principle. But nobody believes that the Hasse principle holds for smooth hypersurfaces of degree 4 in degree 100 in P4. So it's situation is quite bad in this respect. So that's why the conjecture we make is just about rationally connected varieties. It's not reasonable to just say with the Brouwer group. Okay. And so that is proved by using the Gerald formulas, because this condition ensures that H2XOX is 0. And then this condition here, x is smooth, smooth, I should say smooth. And the torsion part here, you take care by using Lefschetz theorem. In fact, the H2x bar Z mod n will be equal to Z mod n. And the constant part, the peak x bar, is just Z. This is a theorem of Max Noether. So Max Noether tells you that if you take a smooth complete section in projective space of dimension at least 3, the pk is just given by the multiple of the hyperplane sections. So that gives you the bar of x divided by bar of k is 0. Now there is an interesting problem. What happens if x is singular? Okay, so this was smooth complete section for which we had this property. Now it's not true in general that if you take a complete section, even a reasonable one, that is, which is not a cone of something smaller dimension, the singularities can create interesting elements in the Brouwer group. And to compute this is a challenge. So a pure algebraic challenge, which we've done in some cases. So for instance, example, if you take x3 in Pn, okay, cubic hypersurface, if the codimension of the singular locus in X is at least 4, I think it's 4, 3 or 4. 3, sorry. No, 4, yeah. Then the bar group of a smooth of desingularization is trivial. So for cubic hypersurfaces, provided the singular locus is not too big, the bar group is trivial. And in that case, we do conjecture the Hasse principle, for instance. And if this condition is false, well, we have counterexamples. Okay, so that's really using the bar group. Now I want to discuss a bit. Sorry, I will stop at 2:30. Some interest in a case which has been quite interesting, which is the case of homogeneous spaces of linear algebraic groups. So this is C. So well, U is of the shape G mod H. Okay. And I'm not going to discuss the case when there's no rational point. I just discuss this case. So G is a linear, connected linear algebraic group. And H is a closed subgroup. Subvariety, a closed subvariety which is a subgroup. Okay. And then so we have U, and then U is in X. So a basic theorem is the case when K is equal to K bar, and it's essentially due to Bogomolov, with improvements by many people, which is that if H is connected, then part of X is 0. This is K equals K bar, so there's no constant part here. So if we take a G mod H, where G and H are linear connected algebraic groups, and you take a smooth compactification, then the bar group of this variety over the algebraic closure is 0. Okay. And I remind you that people were interested in this because it's a big open question whether these varieties are rational of the ground field, or of the C, even of the C. So if the bar group had been non-zero, we'd been very happy. It would say the thing is not rational. Unfortunately, it's always 0. Okay. Bar of X is 0. And then there's a theorem, also due to Bogomolov. This was in the years 1988, approximately, which is the case when H is finite discrete finite subgroup. And then in that case, and you take G equals SLN. In that case, you find that bar of X is given by a very beautiful formula. Bar of X is equal to the kernel of H3 of XZ goes to the product. This is the Combinator of groups. The product for all the abelian subgroups H, A and H of the H3AZ. Okay. So that thing is often called the Schur multiplier of H. So you take the Schur multiplier of H and you look at the classes which die when restricted to all the abelian subgroups. Okay. So that's the formula for bar of X. Okay, now let's look at the case when K is not K bar, which is for number theory more important. So we have K and K bar algebraic closure, G the color group. So here's the notation, piece of notation. If M is a G module, I mean Galois module with stabilizers of points are open, when defined SHA I omega K M to be the kernel of the map from HI of GM to the product for all the possible pro-cyclic subgroup Okay, so you take the Combinator classes which die when we restrict to all the possible pro-cyclic subgroups in G. So G is this enormous group. Okay. So here are formulas. So suppose first to start with that G, T is a K torus. Then K torus is a twisted form of GM to the n. It's got a character group, T hat, which is hom T bar, GM K bar. There's a Galois action in this, it's a lattice. And then the formula is that the unified Brauer group, the Brauer group of X, again, T sits in this smooth compactification. Brauer of X divided by Brauer of K is equal to SHA2 omega K T hat. So you take the character group and you just look at the Galois action on this and you compute the Brauer group simply from the information on the characters. Okay. Note that upstairs we had a similar situation where we had a smooth compactification we didn't know anything about, but in fact we compute the Brauer group just from the data H. So this is the case of a torus. Then there's a following case where you look at the group G, which is semi-simple, but not simply connected. So this is simply connected cover. And this is simply connected. And you have a kernel, which is a finite Galois group. And then in that case, one can compute that. So again, we have G and X, smooth compactification. Then the formula is Brauer of X divided by Brauer of K is equal to SHA1 omega K mu hat. So I'll say a few words about the proofs a bit later. Well, yeah. So this is second case. Third case, I look at G mod H, where so G is semi-simple, it's simply connected, and H is connected. Now, if you have a connected group, algebraic group, there's a maximal torus quotient. So you can, your H, you can divide the Weyl characteristic 0. So I get rid of the unipotent radical, I get a reductive group, then I look at the maximal torus quotient. And then the formula which Kunievsky and I, in fact Kunievsky and I did this one. The formula is that in this case, so what do we get in this case? Yeah, okay. So in this case, one finds that Brauer group of X, so again, X is a smooth compactification. One found that Brauer of X divided by Brauer of K is equal to, which one is it? SHA1 omega, let me call it this one S, K S hat. So in these various cases, you find that formula in terms of T hat, mu hat, S hat, associated to some group of nuclear type associated to the situation. And in fact, there is a general formula. So there was this bizarre thing that with SHA1 here, SHA2 there. Okay. So ultimately, there's a theorem which is proved by Borovoy, Harry, and Demarche, which is that the following: you take G, a group such that peak G bar is 0. Assume peak G bar is 0, and then you take G mod H, and H is connected. Then what you have is that H sits in G, and G has a maximal torus quotient, which I'm going to call, which one is T here. And H itself has a maximal torus quotient, S. And there's a map here. So these are the maximal toric quotients. So from this inclusion, you get a morphism of tori. And therefore you get a morphism of character groups, T hat goes to S hat. And then the formula which they prove is this, is that the Brauer group of X is equal to SHA1 omega of the complex T hat goes to S hat. So you have to use hypercohomology if you want to get a result, where this one is in degree minus 1 is in degree 0. So there's a formula, but the only way you can get a formula is to accept to use a hypercohomology of complexes. So just a few words on some proofs, but not much. So I wrote down formulas for the Brauer group of a smooth complication for a torus, for a semi-simple group. This is for the torus, this is for the semi-simple group, for a quotient of a simply connected by a connected, and then ultimately for a dual situation where we have G mod H and the peak G bar is 0 and the H is connected, and then it involves a hypercohomology of a complex.
So it embeds into the Brauer group of U?
Yes, but we look at the part which is unramified at infinity. That is the challenge. What is the part? Yeah, you can also ask what is the Brauer of U. That's another question, but I won't discuss it now. Okay? It's also interesting. So if you're interested in strong approximation, you bump into questions about computing the Brauer group of open varieties. But here I'm just looking at rational points, so that's why I stick to the smooth compactification. X is smooth compactification each time. I wrote it here. I think I wrote at the beginning, we want X smooth compactification. Okay, so the question is how you prove this kind of results. So basically, tori over non-algebraically closed field are quite important objects. I mean, I think a number of you study linear algebraic groups, so you know that tori are sort of basic objects. And so for tori, have been much studied by Oskosensky, for instance. So there's a fact is that if T over K is split by a cyclic extension, which means that the Galois action on the character group is through a cyclic extension of K, then in fact there exists a torus T dash over K, so that T cross T dash is K birational to projective space. So the tori which are split by a cyclic extension, they are somehow trivial, and so in particular, this implies that if I take a smooth compactification, so assuming this, Brauer group of X divided by Brauer of K will be 0. Because it's true for P and K and it's true for the factors. So tori which are split by a cyclic extension, the Brauer group is trivial. The unified Brauer group, the Brauer group of a smooth compactification. So the one argument I want to show here, since I don't have much time, I want to show one argument, so how to prove this formula, starting from this fact about tori. So this is a formula, let's call it beta, proof of beta. So in the original paper with Kunevsky, we reduced to the case of finite fields. So we have our arbitrary field. We wrote the field as a direct limit of rings of phi type over Z, and then we reduce mod P, we use Chebotarev. In fact, one can do simpler. And so this is what I want to explain. Okay. So proof of beta, I mean, it's using the fact on tori, which I wrote here. So I take my group G, which is semi-simple. Now, suppose G is split. Suppose G has a Borel subgroup, B in G. Okay, so you have this notion of Borel subgroups inside a semi-simple group. Then, in fact, the group G contains an open set, which is of the shape U plus cross torus cross U minus, where this is a torus, and this is isomorphic to a fine space. So if G has a Borel over the ground field, then in fact X, the X, is birational to a torus T across some projective space. And then if I restrict to a procyclic subgroup, so if I have K here, I have K bar, and so I have G here, and I take a procyclic subgroup here, I can apply the result for tori. So my torus T, when I go over to this field, is split by a slag extension. Okay? So its Brauer group is going to be trivial. So I conclude that in that case, this implies that for all H in G procyclic, H1 of H with Z in peak X bar is 0. Okay? If I take a procyclic subgroup, this is the part of the Brauer X bar part is not interesting because we know that X bar is rational. So the only part which is important is the Brauer 1 part, which is given by H1 Galois peak X bar. But if I restrict to this procyclic subgroup, because for the torus, I know this property and peak is birational invariant. So if I have two varieties, sorry, I should say that if X and Y are smooth projective, and they're birational, smooth projective, then peak X bar plus a permutation is isomorphic to peak Y bar plus a permutation. So in particular, in fact, the Brauer group also is an invariant. Anyway, so Brauer group is an invariant, so I can deduce that here. Okay? So I get H1 H peak X bar is 0. So this is assuming that G has a Borel. And now there's a basic trick which you can see used in many places, is you reduce to the case where G has a Borel. So how do you reduce to the case where G has a Borel? Well, you go over to the function field of Borels. So this is maybe you have seen this trick already. So you have the variety of Borels, which is a over the algebraic closure. It's G bar mod B bar. It's an absolutely reducible variety. So let's say called Y is the variety of Borels in G. Maybe it has no K point, but it has a function field K of Y. And if you go over to the function field of this Y, then you acquire a Borel by definition. So you look at the situation K bar, Ky, K bar of Y, and then K of Y bar. The algebraic closure here. So the variety is absolutely, the variety of Borel is absolutely reducible. So you get the same group here, G and G. Let's say here we have a big group G. Let's say here we have a group H. Okay. And now the situation is that peak of X bar is the same because the variety X was defined over K. When you go to these big fields, you do not change the peak R group. So peak X bar is the same as peak of X K bar of Y, which is the same as peak of X extended to K of Y bar. Okay. But now we're interested in procyclic subgroups inside here. Okay. So we have the G here mapping to G mod H. And then we're interested in a procyclic subgroup. Well, I can lift it to some procyclic subgroup here. And then I apply the previous result at the level of this big field to conclude that H1 of my little h within peak X bar is 0. So is this clear? I have this procyclic subgroup, which is a quotient of a procyclic subgroup here. So a bigger one, maybe a bigger one, I don't care. But it's surjective here. So the point is that when you have an extension like this, how shall I put it? Yeah, I mean, we get there's a restriction inflation sequence, which is H1, which will be H1 of H, peak, this module, which is the same for everyone, M, goes to, this is, we take the fixed point, but the fixed point is just the whole module because there's no action here. So this get H1 of the H dash, M, and then we have H1 of something with trivial action. So this is ZR, so this is 0. So that group, I mean, the one of group is 0, so the other one is going to be 0. Okay. So you reduce to the case when there was a Borel subgroup. Okay. So the conclusion is that in this setup, we find, so this is half of the proof. So we find that G in X, we have that for all procyclic subgroup H sitting in G, H1 of H with values in peak X bar is 0. Okay. Now we have G sitting in X. So when you have an open set sitting in a smooth compactification, there's a standard sequence which is the divisor at infinity of X bar goes to peak X bar, goes to peak of the open set. And then here what do you have? Here you have, well, the functions which are invertible on G modulo the functions invertible on X. And this map is onto because the variety is smooth. So this restriction map is surjective. And here we have the invertible functions. But on a semi-simple group, they're all constant. So this thing is K star, K bar star. This thing is K bar star. So we have a short exact sequence in our case. A permutation module, the divisors at infinity, pick X bar, pick G bar. Now pick G bar, it's well known that in a situation like this is just the character group of mu. There's an obvious map from the character group of mu to pick G bar, and it's an isomorphism. So you get the short exact sequence here. So we have 0 goes to permutation module, div infinity X bar, goes to pick X bar, goes to mu hat, goes to 0. Okay. And we're interested in H1k pick X bar. So if I take H1k pick, this is a permutation module, so H1k, so I have H1k, let's call it P hat. P hat goes to H1k pick X bar, goes to H1k mu hat, goes to H2k P hat. And then I look at the restriction to procyclic subgroups. Now this is 0 because this is a permutation module. So in fact I get a 0 here. Similarly I get a 0 here. So I get H product for all the procyclic subgroup H in G of the H1 of H peak X bar goes to product for all the cyclic subgroup in G of the H1 H mu hat goes to product for all the cyclic subgroup H in G of the H2 H P hat. So now the point is that here this kernel is 0. Think of the case where P hat is Z. H2 of a Galois with values in Z is home of Galois with in Q mod Z. And any homomorphism into Q mod Z, which is trivial on the generator, is trivial. And so you have Shapiro's lemma, which helps you to prove this in your case. So you get a 0 here. So you find that the kernel, so from this you get that SHA-1 omega, so that implies that SHA-1 omega K peak X bar is SHA-1 omega K mu hat. But then we saw that these ones are 0 just before. I just show you using the passage to the variety of Borel subgroups that this H1 H peak X bar is 0. So in fact that one is H1 PK peak X bar. And so we have computed the Borel group of X modulo Borel of constant is given by SHA-1 omega K mu hat. So that's just to show you an example of how one can compute these groups without actually writing down the smooth compactification.